More examples. Limit as x approaches negative infinity of t over the square root of 4t squared plus 1. What is it equal to? Well, now we've got a negative infinite number. So t, whoops, I mixed up variables. Let's just fix this. This is, we'll call that t, my bad. So t is a negative infinite number. And we want to investigate this ratio. So the top's infinite for sure. The bottom's infinite for sure. So we're indeterminate form. And what do? We factor out the largest power of t. So t over the square root of 4t squared plus 1 is equal to t over the square root. I'm going to factor out the t squared here. And what gets left behind is a 4 plus 1 over t squared. Not enough to cancel out, but I've got a t squared under the radical. So this is equal to t. And when I pull out the t here, I need to replace it with an absolute value of t times the square root of 4 plus 1 over t squared. And this little piece that I did here is such a common mistake. Students will factor out the t squared and just write it as t. But there's an issue there that, if you recall, that the square root of t squared is the absolute value of t. It's always got to be positive. So in this case, what is the absolute value of t? Well, t is a negative infinite number. So this, in this case, is negative t, right? That's how I could make it the absolute value has to be positive. T is a negative number. To make it positive, I need to multiply by negative 1. So the absolute value of t is negative t. So coming back here, these guys, this is t over negative t square root of 4 plus 1 over t squared. Now I can cancel. So this t cancels, but I still have a negative lurking around. And so this is equal to negative 1 over the square root of 4 plus 1 over t squared. T is an infinitesimal, so 1 over t squared t is infinite, so 1 over t squared is infinitesimal. So the bottom is infinitely close to root 4, so this is infinitely close to negative 1 over root 4, better known as negative 1 over 2. And so that's our limit. The limit here is equal to negative 1/2. So let's play around with rational numbers, playing around with radicals. How about some trig functions? Let's look at the limit as t goes to infinity of sine of 1 over t. So now we're inside of a sine function. We got 1 over t, but we're still letting t go to infinity. So if t is a positive infinite number, then 1 over t is a positive infinitesimal, which tells me that 1 over t is infinitely close to 0, which tells me that sine of 1 over t is infinitely close to sine of 0, in which sine of 0, 0. Therefore, if t is an infinite number, 1 over t is an infinitesimal, and so sine of 1 over t is infinitely close to 0, and that's our limit. Well, not a 6, but a 0. Okay, how about another example? Let's look at limit as t goes to infinity of cosine of t divided by t squared. So if t is a positive infinite number, so t is a positive infinite number. Well, what about cosine of t? Well, cosine, we know, oscillates back and forth between -1 and 1. So -1 is less than or equal to cosine of t less than or equal to 1. So cosine, it's bound above by 1 and bound below by -1. So cosine of t is not infinite. Cosine of t, even if t is infinite, this is not an infinite number. So it's finite, possibly infinitesimal, but it's finite. Now, how about t squared? Well, if t is infinite, then t squared is an infinite number, which tells me that 1 over t squared is an infinitesimal, actually a positive infinitesimal. So then cosine of t over t squared is the same as 1 over t squared times cosine of t. Infinitesimal times finite is an infinitesimal, so this is infinitely close to 0, and we're done. The limit in this case is 0. So the last example I want to look at is looking at another trig function, the tangent function. So the limit, so we'll look at the limit as t approaches, say, pi over 2 from the right of tangent of t. What is it equal to? So now we're looking at t being infinitely close to pi over 2. So t is infinitely close to pi over 2, but it's also bigger than pi over 2 because we're on the right-hand side. So let's investigate tangent of t. So tangent of t, well, tangent is the same as sine over cosine. So that means we actually need to investigate what is sine when we're infinitely close to pi over 2, what is cosine? Well, sine of t, if we're close to pi over 2, is infinitely close to 1. So the top is finite. However, the bottom is infinitely close to 0. So it is an infinitesimal. So I've got a finite divided by infinitesimal, so I know that this is an infinite number. So I know right off the bat that it's infinite. But is it positive infinite or is it negative infinite? So let's maybe bring into play the unit circle to help us get a handle on this. And so if we draw the unit circle here, corresponding to all the points cosine and sine, if we're to the left of pi over 2, so we're bigger than pi over 2, then, right, this is the point cosine of t sine of t. Right, on the unit circle, the cosine is the x-coordinate, the sine is the y-coordinate. So if the angle inputting is bigger than pi over 2, then the x component is left of 0. In other words, it is negative. So we know that if if the input is bigger than pi over 2, so since t is bigger than pi over 2, cosine of t is less than 0, which tells us that cosine of t, since it's infinitely close to 0, is a negative infinitesimal. And if it's a negative infinitesimal, this tells us that tangent of t, we already know it's infinite, but since the numerator is close to 1, i.e. positive, and the denominator is close to negative, or it's negative but close to 0, that this is a negative infinite number, and so we would say this is equal to negative infinity. On the other hand, if we look at, let's continue this. So let's look at the limit as t approaches pi over 2 from the left of tangent of t. Well, we know all the same business, right? Because t is still infinitely close to pi over 2, but now we have that, so t is infinitely close to pi over 2, but t is less than pi over 2. So now in terms of the unit circle, right, because we're going to investigate cosine, sine is still infinitely close to 1, because we're infinitely close to pi over 2. And cosine is infinitely close to 0, again, because we're infinitely close to pi over 2. The question now is, what is the sign of cosine? And so now in this case, if we're looking at our unit circle and looking at an angle less than pi over 2, so this is our t, less than pi over 2, then over here cosine is positive. So we know that in this case, if t is less than pi over 2, then cosine of t is positive, and so then tangent of t is an infinite number, but it's going to be a positive infinite number, and so this limit is positive infinity. And with that together, we would say that in general, the limit as t approaches pi over 2 of tangent of t does not exist. It doesn't even approach one of the two infinities. And that shouldn't be too terribly surprising. Hopefully you know what the graph of tangent looks like. So we've got asymptotes, in particular at pi over 2. We have asymptotes. And the graph of the function as it approaches from the left, well, that's what this is saying. As we approach from the left, the function is going to positive infinity. So we know that tangent has to go like this as we approach from the left. And as we approach from the right, it's got to be coming from negative infinity. And that should fit your sense. We know actually tangent looks something like this, and it just repeats itself. So that should fit exactly the graph, hopefully, you have in your mind of tangent. Okay, that wraps up chapter or section 5.1. Really, all that's going on is we're bringing back into play all of the algebra and arithmetic we developed back in chapter 1 for working with infinite numbers and infinitesimals, and in particular, how do you deal with indeterminate forms. And hopefully this, if you struggled the first time, the second time around it's becoming more clear. And all we've thrown in the mix is the formalization of using limit notation to investigate these behaviors. So keep on working hard, happy mathing, and see you next time.